let's start the class. One announcement before we begin. I'm going on a trip for the Labor Day weekend, but I mistakenly bought my return ticket for Tuesday. So I'm going to be here on Tuesday, 7 p.m., which means that we won't be able to have a class, right? So the class on the theory of buckling. Did we cover theory of buckling in lab 1 at all? We didn't, huh? I don't think so. Yeah, we didn't do this. So, and have you studied, have you heard about buckling at all?
Just mentioned in 101.
Here and there.
Mentioned in 101, that's it.
Yeah.
So no, in mechanics of solids you don't have any buckling, did you? Okay, so we definitely need to talk about buckling a little bit, because buckling is a very important phenomena in aerospace industry in general, right? It's one of the more important failures. I mean, you don't really have any yield failure when you're flying the plane. The buckling failure, it may happen. So that's an important lecture that we are going to miss, right? It is either, we have two options for that specific lecture. I can either record it and put it on Blackboard, so you can go and watch it, or we can meet on the Wednesday morning when we are supposed to meet. And I see some heads turning, right? And some heads, moving, shaking. And so, let's actually take a vote on it.
Oh,
Wednesday or online?
Does that mean tomorrow?
No, not tomorrow. Next week. Next Wednesday.
The question is, when is the actual lab happening?
Tuesday, sorry. So if we do the lecture, we can actually do the lecture tomorrow as well, tomorrow morning.
I'd rather do it recorded.
What's that?
I'd rather watch the
So let's take a vote on the three options. Tomorrow, and the second option is online. The third option is next week's Wednesday, in 8 days. Option 1. Who votes for option 1? No one wants to see me tomorrow. That's all right. I guess you all have to.
I already see you twice tomorrow. Yeah.
That's right. You have 9 credit hours with me. I can bring down your GPA to a D. Okay, that's good to know.
It's too much power.
It's too much power, yeah. And so no vote for tomorrow. Well, online. Guess everyone. Okay. Okay. So I record the lecture. I'll probably record it sometime tonight or tomorrow morning, and put it on that YouTube channel you're all familiar with, and I will share the link with you guys. Make sure to watch the lecture, and I have made sure my TA is also well aware of the buckling phenomena. He knows everything about the test. The test we are going to do is a very simple test, right? But I just want you to be familiar with the theory behind it. Right? The theory is the more important one. Just have to be aware.
Are we moving at time of the actual testing of the lab?
I didn't hear you, I'm sorry.
Like, we're moving the actual lab testing? Like, since this is the lecture, when are we doing
That's 4:50.
But you said you're landing at 7 p.m. on Tuesday.
Yeah, but my TA is
Oh, he
going
will be the one.
Yeah.
Okay, cool.
That's I usually, I think you remember that I usually come to the labs, but I'm not supposed to come to the lab.
Gotcha.
It should be a TA's job, but I do a lot of micromanagement, so.
Is this one as good as Sarab?
What's that?
Is this one as good as Sarab?
No, Surab hasn't already left, but he's going to leave pretty soon. He has already defended his thesis, yeah.
Is this new TA as good as him? Or as good as he was for Lab 1? Sarab was a pretty good TA.
So, are you talking about his personality, his knowledge, or his ability to speak English? Which part are you talking about? He was good on all of those. So.
How lenient he is about grading.
Yeah.
Okay, so Surab was lenient about grading. I didn't know that. That's.
He was.
Huh?
He was joking.
Yeah,
That's. I will double check the grades. No, as far as the grading goes, I don't know. So this new TA is an international student like Surab was, but he just came to the US 2 years ago. So his English is not as good as Surab's was or is. Which I don't think is gonna bother you. He's fine communicating. His English is very good. He was an English major, so he should know more English than all of us combined, man. At least the grammar. And his knowledge, I can't really talk about his knowledge. I mean, you should ask him questions. See, you will be the judge at the end of the semester. I will actually ask you for evaluation. That's going to be my policy from the semester onward. I wanna evaluate the TAs to make sure you have the best experience. But your TA, yeah, your TA was Surah, wasn't Fatima. Okay, any questions?
He's an English major, now he's graduate engineer?
It's a very
It's a 180.
interesting situation. What's that?
That's a 180.
That's it. You can talk to him about this. Don't want to get into his personal life. But we are from the same country. We are both Iranian, from an enemy country, I guess. Iran is like an enemy country to the US, isn't it?
Oh, like being a hate country, kind of how Russia is. Yeah,
I guess, yeah. You are from Russia, right? You are from an enemy country too. Yeah. You should form an alliance. So I guess you're gonna meet him today or next week, depending on how soon we finish the lecture today. If we finish this lecture soon enough, I'm gonna call him up and we can go downstairs to the lab. He's probably gonna be in a class, so I don't think he can join us. But then we are gonna meet him next week. And is there any other questions? No. Okay, so let's go ahead and start the discussion. Hopefully, we are gonna have a very quick discussion on statistics. Make sure to ask any questions you may have. Let's talk about the lab a little bit. Today's lab is called the Uncertainty Lab. The uncertainty analysis is a very important analysis in engineering. Whenever you are dealing with any sort of measurement, you have to do uncertainty analysis on your measurement. And why is that the case? Because with your measurement, you will definitely have some sort of an error. And you should be able to identify that error, and you should be able to find the confidence interval in which your true measurement will lie into, right? Are we familiar with confidence interval? So, there are two specific type of errors, or accuracy, if you will. We have accuracy of measurement, accuracy of measurement, and we also have precision of measurement. Okay, who can tell me what does accuracy mean? What does precision mean?
I can't remember which one's which, but I know one is that all of your data points are around the same value, and one of them is that your data points are around the correct /
The
desired
true value. Yeah. Which one is which though?
I want to say accuracy is the true value, precision is that they're just grouped together.
Did you want to say the same thing?
That was the other way around.
It could be.
I always mix things up myself as well.
Accuracy is like the
I think
good thing,
Lawson's
precision
right.
is the true. Yeah.
I think precision's just together, grouped together in a little
Oh, yeah.
somewhere else. And then
You are actually Lawson and Nick are correct in this one. So precision refers to how precise or how consistent your measurements are, right? So more consistency in measurements will result in more precision. And accuracy refers to the deviation from the true values of the data, deviation from the true value. Okay. So this essentially means that we are going to have different types of errors, and not just the two errors. There are many different types of errors. Errors can include your breathing error, like in the experiment we are going to do later today. We are going to use calipers to measure the length of a block, right? That you may have some error in reading the number off of the caliper. You may have some problem in like measuring the actual length, because it has to be a straight line, right? It may be a little deviated from, there may be a little deviation from a straight line, so that will cause some error, right? All of these things, there may be some fluctuations in the size of the cylinder. A lot of factors will go into causing error in the measurement, right? And the reason this is a very simple lab. The reason we do this is because I just want to focus on the uncertainty part of it. I wanted to make sure that you are clear on this, you know how to do the calculations, and you understand that if you are measuring something, you have to present your measurement as a confidence interval. You cannot just measure one value. If you're measuring like the flow rate, you have to do it 10 times, 15 times to make sure you are getting consistent values, right? Okay. So that essentially brings us to the repetition. We have to repeat the measurements as much as possible to have a set of data. But the question I have for you here, to continue the discussion, the question I have for you here is this: can we ever measure the true value of something? It is always an estimate. So whatever you measure is always going to be the estimate. So your data can be, or your measurement can be represented as your estimate plus minus the uncertainty. So let's talk about this estimate first. The idea was to have a better representation of your measurement. Whatever value you want to measure, you have to do a couple of measurements. Right? But which one's going to act as your estimate? So we have one answer that says sometimes the mean value of those measurements is going to act as your estimate, right? What else do we have?
I think depending on the subject, or the purpose of the experiment, in a broader sense, you could kind of pick it depending on what you want the outcome to be, but that's manipulation of data. But if you have a plane that you need, maybe you really want it to be sold by, or like you have a deal set up for it, and one estimate looks better marginally than the other, choose the other one.
So you said a lot of things that I have a lot of issues with, right? That's a good thing you brought this up. As an engineer, you want to be true to the formula. You want to have the best accuracy possible, right? As a salesman, right, you want to sell the better looking data, right? So you just have to decide which one you are. I mean, at some point in engineering, if you're in the industry, you're calling someone, you want to convince them to buy your thing. You are going to avoid the data that doesn't look good, right? That's for sure. That's how it happens, right? But as an engineer who is going to design something, like who is going to design the control system on a Boeing 787 MAX 8, whatever that is, right? You want to make sure that you are not cooking data, right? Okay. So, but that doesn't really whatever you said didn't really answer on what else can be used to represent the estimate other than the mean.
Median definitely has a place in data sets. I mean, if you're looking at average salary of the position, and you're looking at salesmen, some of them top out at 7 figures, and some of them start at 20,000. There could be like 100,000 salesmen out there making 20,000, and there could be 12 making $1 million. That's going to skew the data way up to the $400,000 range.
Exactly.
So median
Exactly.
means a lot more for like house prices, salaries, stuff like that.
And so depending on the type of data, sometimes you represent your estimate with the median instead of the mean, right? What is the last thing? I mean, there are a couple of other things, but what is the last more common thing you use to represent the data? Mode. Exactly. This is what I'm
Second grade. Let's go.
I was thinking like what we did in vibrations, where it was like a mixture of all of them.
Okay. But for our data here, we are going to use the mean. Right? How do we calculate the mean? Your mean, x of m, is going to be 1 divided by the number of data you have, and the summation of all of your measurements. Right? It's pretty simple. You have seen this many times. There is another type of mean which is called the geometric mean. Geometric mean is usually used. I've never used geometric mean in my own analysis because it is usually used in the financial analysis and also biological studies. It's essentially nth root of the product of n numbers, right? So instead of adding this up and then dividing by the number, just multiply all of your x1, x2, 2xn, and then take the nth root, right? That's a geometric mean. The geometric mean? Okay. It is, we are not really familiar with this, so that is why it looks weird. Oh, you don't remember, you're going to have your first quiz this week, right? I should double check on the syllabus. Let's just make sure we are going to have the no. Okay. We don't have any quizzes. That's a shame. I mean, it would have been a very easy quiz.
Buff my quiz stats.
Easier than what happened?
It's funny how we just didn't have those last time we
I mean,
That was a great time.
That was fun.
Maybe that might happen this semester.
you never know. It really depends on how lazy I feel. But,
Waiting for
okay. So we already know how to represent the estimate. But how should we represent the uncertainty? A standard deviation, exactly. What does a standard deviation represent? Sigma. Let me actually give you the formula first. A standard deviation is 1 divided by n. Sigma n equals to 1 to n xi minus xm to the power 2, right? So this is a standard deviation. Or root mean squared deviation. Okay. What does a standard deviation represent, though? The extent your data point deviates from the mean, right? Okay, so why don't we just use this equation for a standard deviation? Because we want to find the deviation from the mean, right?
You get negative values. So you can have an actual zero standard deviation.
Can you repeat the second thing you said?
So you can have a zero standard deviation with only
Exactly. So the main reason we use this formula of a standard deviation is because with this one we may have a zero standard deviation. Look at the normal distribution. How does a normal distribution look like? Bell curve, exactly. So let's take a look at the normalized bell curve. And let's say this is your mean, right? And we have normalized it, so your mean and zero or whatever, right? The standard deviation, if we use this formula for standard deviation, we are going to get 0 for standard deviation, right? Because the deviations cancel each other out. And we don't want that to happen because we can obviously see that the normal distribution, there are a lot of data points that deviate from the mean, right? And we want to have that deviation. Okay. So we are going to use a standard deviation to represent the deviation from the mean of one measurement. Okay. But let's say in order to make this more accurate, let's say we measure 10, we have 10 data sets. So we measure something 10 times, calculate the standard deviation, calculate the mean, and then we do it the second time, third time, fourth time, 10th time, right? Isn't that going to make everything more accurate? You have more data points, and I'm assuming the confidence interval, you will be more confident in your confidence interval, right? That makes a lot of sense. And there's actually a methodology that is going to help us do this without making 100 measurements, without creating 10 data sets, right? How do we do that? That's actually pretty simple. We call it finding the standard deviation of the mean. So essentially, we are going to take this 100 measurements, 100 data sets, then we want to calculate the mean for all of those. Then we want to find the deviation of those means from the data set's mean. That does it make sense? So we are doing this calculation many times. The standard deviation of mean is essentially simply going to be your standard deviation of one data set divided by the square root of number of data points you have in one data set.
That's a lowercase sigma, right?
Yes. Is there any questions so far? So if you want to find your, you want to represent your measurement, you have to represent it with the mean of your data set with the sigma divided by n. Okay. And this is going to give you 100% confidence interval, meaning that whatever value you measure, whatever value you may have, whatever your true value is going to fall into this confidence interval with no doubt. It will definitely fall into it. But the problem is with this is that your confidence interval is going to be very, very large, right? Unusable. It is going to be useless, right? So large it is. So what can we do for this, to resolve this? We can actually limit the confidence. We can say, okay, let's find the confidence interval that gives you, for example, 85% probability that your data is going to fall into this region, this deviation, this much deviation from the mean. Does this make sense? So instead of, because that, let's think about it. The idea is this never ends, right? The idea is this is an asymptote, right? This never ends. So a confidence interval that will definitely include the true measurement is going to be impossibly large, right? So we need to come up with some methodology to limit this. And this is the way we came up. We just say the probability of true measurement, let me write this down, falling into the confidence interval is, for example, 85%, right? And it's going to give you 85% chance that your true measurement is going to be in this shaded region of the normal distribution. And this probability is actually defined by something called the Z-score. Okay? Are you familiar with the Z-score? Right? Okay, so if I tell you that I want this confidence interval to have a 95% probability, right? Or 95% confidence. You have to find the Z-score that corresponds to 95% confidence and then represent your data using this equation. Z multiplied by your standard deviation. And this is the Z-score. This Z-score actually comes from the normal standard deviation. Just to give you a background, are we familiar with the background of Z-score?
No.
So.
What's that?
Sure, I was at some point. I used to know.
Okay, so we have the normal distribution, right? Which goes up to 1, right? And x of m is actually 0, right? You remember this? The normalized normal distribution. The idea is that 2/3 of your data is going to fall into this, right? And then you have the 1/3, 1/3 of the data is going to fall into this. 2/3 of your data is going to fall into this region. And the Z-score of this region is going to be a given value is going to be 1/3, right? And the Z-score of this value is going to be 2/3, and so on and so forth, right? That's how we calculate the Z-score. So to a standard Z-score of this, Z-score of this is going to be 1. Z-score of this is going to be 2, right? So how much of your data is actually you are going to cover? That which corresponds to your confidence interval. Any questions so far? Okay, so we already know how to use the Z-score. I didn't want to go too deep into the Z-scores and everything, but we actually have to read the Z-scores from the table. The tables are in the, let me see if I have this open here. Actually, I can't open it. The tables are in the notes. You can actually I know statistics can get a little boring, but it's very important. So I'm sorry for boring you guys, but this is how it is. Okay. Yeah. The Z-score table. Who can tell me how we can read the Z-score table? Confidence interval? Yeah? No, that's for the T-score. Yeah, that's for the T-score.
How many samples do you use?
Eta. Okay, so think of this as an assignment. To read this table, I'm pretty sure it's pretty easy. It will come back to it. It's not that hard. It is going to be so easy to do this. I actually explain a little bit on this notes, but the reason I asked you to do this on your own is because I want this to be a little, I guess, hacked into your brain. I want this, because whenever you see a Z-score table, you should be able to do it. Okay, but the Z-score is valid, for we can actually show this mathematically. The Z-score analysis is going to be valid for whenever we have enough number of data points, more than 25 specifically, right? Based on the range and everything. What if we don't have enough number of data? Then, as Igor mentioned, we are going to have to use the T-student method, which essentially talks about the exact same things as the T-score, but with a lower probability for the confidence interval, right? And for this, using this student T method, we are going to represent the data as x of n plus minus T S divided by standard deviation divided by the square root of n. Okay, let's go to a T-score table and see if you guys can tell me how to read a T-score table. Where is my PDF? Okay. How can we read the T-score? Yeah. It's going to give you the T-score, right? And then yeah, that's this. I've said 75%. Should have been 95%. But I mean, you don't have to do 95%. You can. I'm pretty sure you can find the 75% tables. And there are millions of these tables on the internet, right? If you couldn't find it, send me an email. I will provide the table to you. Okay. And if you want to do any other confidence interval, I'm fine, as long as you know what you're doing, as long as your calculations are correct, right? And that is always a deal when you are. I mean, you have had too many courses in already, so you do know this. Okay, so, and this is n minus 1, the number of data points. The degree of freedom is going to be n minus 1, right? Okay, so at this point, we are going to, let me go back to the, at this point we already know that we are going to make 3 measurements, right? We are going to measure the length, the height, and also the width of a block, right? That's the experiment, that's what we want to do. One side of it is supposed to be 1 inch, another side of it is supposed to be 2 inches, and the third side is supposed to be 3 inches, right? And you have to make like 30 measurements. You have to provide the confidence interval, and so on and so forth. But at the end of it, you have to calculate the volume. And this is the part that is actually the most important for you guys in engineering, because we don't really work with raw data. We do some analysis on them, right? We multiply them with whatever, right? We do something with them, right? What happens to the uncertainty after you do some calculations on your data, right? So we need to calculate the volume of this block, right? But how should we represent the data? Whether we have uncertainty, that's for sure. How does the error or the uncertainty propagates throughout the volume, right? That's the thing we need to answer. Is there anyone who does know the answer to this question? Are you looking at Igor?
Yeah.
It's
He
like,
knew the T table.
it's like
already.
different for division and subtraction, you know that much, but some of like a derivative.
The error is bigger.
Error is bigger.
If you have to multiply two numbers with error, then the error becomes bigger.
Is it like
So do we have to just multiply the uncertainties? Is that what you're saying?
I guess when you multiply two numbers, the error would probably be both when both uncertainties added together.
Added together. Okay.
I think it's multiplied. Like if you've got like 75%, 75%, you get like.
But that's going to make your error smaller, doesn't it?
That makes your.
Like let's say it's 1 plus 0.01.
I think it's an exponential growth.
I'm very sorry. I have to take this. I'm very sorry for this. I'm very sorry. Hello?
You got
Think about it
75%.
like two
Okay.
choices at a time. If you choose the wrong
Yeah,
one
yeah, yeah.
first off, then every single time you choose your further
Yeah,
and
calm down,
further
yeah.
and further away, so the error gets bigger. But you get exponentially
The
more wrong.
uncertainty gets.
My wife actually
You divide them.
So,
So you add it together. I'm pretty sure it's exponential.
I'm sorry, guys. I'm sorry. This guy was supposed to pick up something from my home, and they told me 11 to 5. I was like,
That's a big gap.
that's a very,
It's a whole work day.
that's a lot of uncertainty, right?
That's a lot of uncertainty.
Exactly. So, how does it propagate?
I say exponential.
Exponentially. How do you calculate that propagation, though?
I think whatever.
Well, you have to be able to present data, right? Just saying that we're going to have more error doesn't really work here.
I'm almost sure it does get exponentially larger, but I'm not sure what that exponent is. Because like the way that I'm trying to think about it is if you have an error and then you, in this case, multiply it, then it doesn't. It's not the same factor as far as how far away it goes. So the error grows the more you mess with it.
Error grows.
I've settled on division.
Deviation.
Uncertainty gets larger.
Okay. What else? Do we have any other opinions from Trey, Igor, and Nirlev? No? No? Nothing?
something to do with like everything.
Okay, he wants to say something, but he doesn't want to.
I don't know, I just looked at
Okay, so whenever you have, what is the function of this volume, this specific volume? Volume of your block is going to be length multiplied by height multiplied by depth, right? Whatever you want to call it. X multiplied by Y multiplied by Z. And this is a function, this type of function is the kind of functions we are going to deal with in engineering, right? So whenever you have a function of independent variables, that's the very important part. So your variables have to be independent for this method. Dependent variables is another ballpark, right? And we are not going to get into it. Whenever you have the function of an independent variables, r is equals to a function of x1 to x of n. Doesn't really matter how many number of variables you have. The uncertainty of r, w of r, is calculated by this function. The derivative of r is with respect to x1, your first variable, multiplied by the uncertainty of that x, right, to the power 2, plus derivative of r with respect to x2, multiplied by the uncertainty of that second measurement to the power of 2, plus the derivative of r with respect to x3, xn, whatever. What do you think? What is the difference between? Doesn't matter. What is the difference between a partial and full derivative, absolute derivative? We had we had a question and one person said doesn't matter. So you have to justify your answers.
To be honest, they never really spelled out the difference for us. They just kind of put it up partial and said this is not a full derivative and moved on.
Okay. You are justified because you asked the question, but you came up with an answer. You have to explain your answer.
Because they're functionally the same, at least in the formula.
Why? That's what it means.
So what you're saying is that they are taking the derivative, right? That's what you mean.
Essentially.
Okay, but it does matter though. Partial derivative refers to the fact that this r is also a function of something else. Like x2, in this case x2 to xn, right? But the absolute derivative is just a function of one variable, right? I'm really happy this was brought up.
It's just like
Yeah, that's. Okay. So this is the equation. So for our case, when we are calculating the volume, I guess it took a little longer than 10 minutes. But for our case, where we are going to calculate the volume, how would this uncertainty look like? W of your volume is going to be equal to, what is the derivative of r or volume with respect to x here? Your x1 is x, y and z, and this is the mean value of your measurement of y and mean value of measurement of z, right? Multiplied by the uncertainty of x calculation. What about the second part? Derivative of r with respect to y is going to be xz multiplied by the uncertainty of y, and the last one is going to be the derivative of volume with respect to z, which is going to be xy multiplied by the uncertainty of z calculation to the power 1/2. So you make the measurements, 30 measurements to be exact, from each side, so 90 measurement total. You use those 30 to calculate the z-score for a specific confidence interval that you are told in the lab instructions, right? And then you do the uncertainty analysis. You calculate this once, you calculate the volume using the mean values, and you also calculate the error propagation, uncertainty propagation, right, using this formula. And then you do the t-score analysis. But there's a catch here. What is the catch in the t-score analysis? Exactly. So essentially you have to use at less than 25 of your readings, right? Is there any questions here? Yeah, error propagation is actually a very, very important topic in in any engineering field actually. It doesn't really matter if it's a numerical or experimental field. When you get into numerical field, there are books written on error propagation and how to deal with this. But that's a different error propagation. It's the same idea, but it's a little different. But I guess that's it. Is there any questions? Okay. Let me stop the recording.